Hey, good morning, everybody. Really nice to be here. I mentioned before, this is really my favorite workshop. This is great to see all of you. Yeah, so more about Hungatonga this morning. I'm going to talk about an approach to doing tomographic retrievals of Hungatonga volcanic aerosol using the OMSLIM profiler. Especially Daniel Zawada and Landon Rieger, who many of you know were really important to this work. Daniel Zawada's not here this week because his baby was born yesterday. So yeah, this is first, they had a girl. Yeah, and also Doug, of course, has been very important to this work in a way. This is an evolution of the tomographic work that Doug started more than 20 years ago with limb measurements with OSIRIS. And just to be clear, since some of you think this is still the case, Doug is not my boss, although he used to be, but he is not my boss anymore. Okay, so we've seen lots about Hungatonga already. One paper that hasn't been mentioned yet is this paper by Sergei Kakin, which I'll just call your attention to. It's published in Communications, Earth and Environment. It's a really nice sort of meta-analysis of Hungatonga. It talks about both the water vapor and the stratospheric impacts of the eruption. I like this bottom plot especially, which is the aerosol AOD time series for a long time. Basically, this is the GLOSAC record, and with Hungatonga here at the end, and you can see it's really quite large. The paper says a 4 to 5-fold increase in stratospheric aerosol optical depth, exceeding any event in the last 3 decades, although the inset here shows it with respect to Pinatubo, where it's still, it's quite small with respect to Pinatubo still. Okay, so there's lots of questions. Some of these are being answered already by the papers that are coming out and by the nice talks that we've had this morning by Ghassan and Travis. What's the spatial and temporal extent of the aerosol? Do the observed levels correspond to the observed SO2 emission? That's an interesting one. Does the water vapor affect the aerosol microphysics? I think we're seeing some convincing evidence of this already. And what is the climate impact, especially in the stratosphere? And of course, limb sensors, our favorite instruments, are very critical to answering these questions. So for today, I want to talk also about the OMSLIM profiler. This has really been an important instrument for monitoring the amount and spread of the volcanic aerosol from Hungatonga. Some papers talk about this. Ghassan showed us some of his nice results here already this morning. What I want to show is that the rapid imagery that OMSLP is able to make actually enables a tomographic retrieval of the aerosol. And this does improve the agreement of the retrieved aerosol with Calypso and Message. And it actually makes a difference. This can cause a bias of up to a factor of 2. And this is not just in the early plume, but this really extends for months afterwards, especially in the integrated values like SAOD that we like to use for our analysis. And there's also additional uncertainty, of course, in limb scattering. We're always concerned about the particle size distribution. So yeah, we've talked a lot about limb scattering already in this workshop, but we haven't talked too much about the radiative transfer, so I want to talk about that just a little bit to set the stage. Of course, we need a complex forward model to handle the multiple scattering processes in the atmosphere. This has to handle the atmosphere-to-atmosphere multiple scattering, as well as the reflection from the Earth's surface and then subsequent scattering in the atmosphere. So here I show the integral form of the radiative transfer equation. The source term, which you have to integrate along the line of sight, has to do with the light that's scattered into that point, which depends on the scattering phase function when there's aerosol, right? And that scattering phase function is really the link to the particle size distribution. This is what changes in the radiative transfer equation as the aerosol particle size changes. So that's where particle size comes in. Okay, about the tomographic retrieval. So we do an aerosol retrieval algorithm very much like we've done with OSIRIS for years, where we retrieve an aerosol number density for an assumed particle size distribution. We use our favorite log normal particle size distribution, 80 nanometers, 1.6 mode width. This lets us define the scattering cross-section, but the product of the cross-section and the number density is really the extinction, and that's what we report. So what's left in the radiative transfer equation is the scattering phase function that comes from this assumption of particle size. We do the retrieval just for a single wavelength channel at 746. I think maybe Alexi convinced me yesterday a different wavelength might be a better choice, but it is what it is. We've done it at 746. Now, the nice thing is we've done this tomographically with a 2D retrieval grid. So you can see here this sort of cartoon that Dan Zawada made where ALTIUS is in orbit making images every 19 seconds. The tangent points of the image slant upwards towards the satellite. That's just basic geometry of the limb. And you can see that these are spaced about every 125 kilometers along the satellite track. And what we traditionally do in limb, right, is we take one radiance profile and retrieve one aerosol profile. But when you have rapid imagery like this, you can set up a two-dimensional grid, a grid that moves along the satellite track and in altitude. So for each one of these grid boxes, then you combine all the images that sample that grid box and you retrieve it tomographically. So you don't end up with one image, one profile, but you end up with this two-dimensional retrieval grid along the satellite track. And that helps you resolve some of the geometrical artifacts. And I'll show you that here. So this is one orbit of ALTIUS data from 60 south to 60 north. This is altitude. And what I'm showing here in the color scale is the retrieved extinction. And this is the tomographic retrieval algorithm we've done at USask compared to the baseline NASA retrieval. And what you can see is where there's localized aerosol in the stratosphere, that if you do a classical one-dimensional retrieval, you get this kind of U-shaped artifact, right? And that's just geometry. That's the limb line of sight picking up on the far side of the tangent point, at the tangent point, and on the near side of the tangent point as it goes through the layer. And the tomographic algorithm is able to account for that geometrical effect and better localize the aerosol. And so if you take some slices through this, you can see at 24, 22 kilometers that the USask algorithm is measuring higher values of extinction. And below, if you take a slice underneath, that the NASA value is measuring higher values because of this sort of two-dimensional geometrical artifact. I'll show you another example. This is just another orbit, one a little bit later in time with a little bit less aerosol. And again, you can see that the tomographic algorithm is able to sort of better localize the retrieval of the plume. And it's not perfect. You can still see that there's some sort of trails that are hanging down here. The method has told us that this is converged, but little things like stray light, tangent point registration, things like that will ultimately still cause a little bit of systematic error. Okay, so every once in a while, and I think Jeff Landon mentioned this, every once in a while, the ALTIUS and Calypso orbits align really nicely. And so this gave us a chance to see just how well this tomographic retrieval algorithm is doing. This is a daytime measurement from the Calypso LiDAR, and you can see, even though it's a strong aerosol layer, in the daytime, Calypso can kind of barely pull this out of the noise. We have to use the daytime measurements because that's when ALTIUS is measuring in the daytime. But you can see the layer here, and if we degrade the Calypso measurement to ALTIUS resolution, it looks something like this. Okay, so now let's compare that to the ALTIUS retrieval. So here we have Calypso daytime, Calypso at ALTIUS resolution, the tomographic retrieval, and the standard retrieval. And I think it's quite convincing that the tomographic retrieval is doing a nice job and getting closer to what Calypso is measuring with its nice high vertical resolution. Okay, and ultimately this impacts the integrated values that we like to use, like stratospheric aerosol optical depth. So if you just calculate the vertical optical depth from 18 to 30 kilometers, zonally average from 25 south to 10 north, and make a time series, you can see that there's actually quite a bit of difference that persists for quite a long time. So this is causing a reasonably big effect. Then if you subset that to within plus or minus 1 degree of the latitude of a SAGE measurement for that day, you get the bottom plot here. And of course, SAGE is kind of sampling in and out of this latitude band. And the SAGE measurements here are shown in black with gray lines connecting the dots. And it's really it's a bit of a mess. It's really quite hard to make out what's going on there and convince yourself that one is doing any better than another one. So if we continue that analysis with SAGE, where we're only looking at coincidences within 1 degree of latitude, nice tight coincidences, but now just look at extinction as a function of altitude, and plot the difference in extinction between ALTIUS and sage and the NASA ALMS product and sage, you can see two things. You can see that underneath the volcanic plume, that the NASA product is overestimating. This is this artifact of the blurring. But in the peak of the layer, both products are systematically too low. And we think that's due to the particle size assumption. We're not allowing the particles to change in the retrieval. Travis showed us that the particles get quite big, and that's causing a systematic error. So we looked into this a little bit. What we're showing here, these are kind of complicated plots, but on this axis is the ratio between ALMS and sage. This is the ALMS-USAST product. So where it's 1, the two products are agreeing really nicely. And on this axis is a median radius retrieved from the sage 3 extinction spectra. This is a median radius retrieved assuming a mode width of 1.6. This actually converts to an effective radius around 400 nanometers, very consistent with what Travis showed us this morning. For these values around 175. So, okay, so this is below the peak of the plume, 18 to 21 kilometers. In blue here, we're showing where the extinction values are less than 0.004. This is basically background levels of extinction. We're seeing background levels of extinction below the plume, 18 to 21 kilometers. ALMS and sage ratio is 1. They agree nicely. The median radius is around 100 nanometers. Not so different than what we assume in the retrieval. Now, if you move up in altitude, where the Hunga-Tonga plume is, now the ALMS-sage ratio is, not very good. It's like a half. We're underestimating by quite a bit because the particles have grown up to almost 200 nanometers in median radius. Okay, so if you go later in time now, so now this is from June to September, more towards the last half of the year, now you see high levels below, kind of below where the peak of the plume used to be because it's settled, and you still see them up high. And now it's a little bit more complicated case where we're still seeing ratios of 1 at unenhanced values of extinction. At enhanced values of extinction, the ratio seems to be coming back towards 1, is not as bad as it was before, but it's a messier picture. So I think I don't really know what to draw from the conclusions from this other than things are relaxing back to their background state mostly, but it's still not super clean picture. Okay. So I'm almost done. I just wanted to point out something that we've seen a little bit already today. This is a zonal average, ALMS extinction, altitude by time, all the way up to May of this year. And this is a big bin. This is from 0 to 50 south. And Bill Rantle sent me a picture that his group made that looked very much like this. And Bill said, hey, Adam, what's going on here? Because it looks like the ALMS extinction is kind of growing with time. Like you see this sort of like delayed maximum. And so I thought, okay, I don't know, maybe that's the bias, this particle size thing that we're seeing that's shifting over time. So I made the sage plot, and I got a plot that looks very much like what Travis was showing this morning, where in this big latitude bin, sage is, doing its sampling thing. So it's sampling the tropical plume, the extratropical plume coming in and out. You get a picture that looks like that. And it's hard to see, right? So here, sage is in a part of this latitude bin where there's no volcanic aerosol. And here there is volcanic aerosol. And here we're just doing a great big zonal average of the same bin. So you have to be really careful with the sampling here. But I was still curious about this, what is this maximum going on here? And I think it's just a sampling thing. If you look at now, so here we have time, and here we have latitude, and we're just showing the aerosol optical depth. The circles and diamonds are the sage occultation points, colored by the sage stratospheric optical depth, and the underlying color scale is the ALMS stratospheric aerosol optical depth. So here's Hunga-Tonga. You can see some really hot sage points there in the first early part of the plume, but then as the plume shifts down here into the southern hemisphere, like Ghassan showed us, you see higher values again. I'm not exactly sure why that is, but I think that's real. That's part of the transport. There's several modeling papers like this one from Liu et al., which just came out in GRL, that shows that as the plume moves into the southern hemisphere, I think Alexei showed something like this as well, that you see another maximum here. I think it's just transport. So message there, just be careful about the sampling and the interpretation. So conclusions, tomographic retrievals improve agreement with Calypso and SAGE. That can cause some biases if you ignore this effect that extend beyond the yearly plume. There's still uncertainty in the particle size distribution, which causes some bias. You have to be careful with sampling, and you can check this out in GRL. Last thing, this episode is brought to you by Sastran. This is my advertisement for our radiative transfer model. This radiative transfer model we developed starting years ago, even before OSIRIS. It's a fully spherical model. It's very fast. It uses successive orders of scattering solution. There's also Monte Carlo and LiDAR modes. There's 2D, 3D atmospheres. You can run it in polarized mode with a full vector solution. And we've tried pretty hard to make it easy to use. There's built-in cross-sections, there's built-in climatologies, default atmospheres, lots of example code, built-in aerosol and cloud phase functions, and an easy-to-use Python installation. So give it a spin. Thanks very much.